Imagine a world where the way we understand categories, games, art, emotions, even species, isn't based on rigid definitions, but on overlapping similarities. This isn't just philosophy. It's the foundation of a new kind of machine learning algorithm, one that thinks like Ludwig Wittgenstein. In 1953, in Philosophical Investigations, Wittgenstein introduced a radical idea, family resemblance. He challenged the notion that categories must have a single defining feature. Instead, he argued that members of a concept, say, games, don't all share one thing in common. Rather, they're linked by chains of partial overlap. One game shares rules with another, another shares competition, another shares entertainment. No single trait unites them all. But together, they form a network, like a family where cousins resemble each other through shared traits, even if distant relatives don't look alike. Now, fast forward to modern machine learning. We're still trying to cluster data, grouping similar points together, using algorithms that assume clusters are spherical, convex, or known in number. But real-world data, it's messy. Spiral-shaped, intertwined, nested. Traditional methods fail. So what if we built a clustering algorithm not from math alone, but from philosophy? Enter Wittgenstein's Family Resemblance, WFR, clustering, a novel graph-based approach that doesn't rely on assumptions about cluster shape, number, or even metric structure. Instead, it mirrors the way Wittgenstein saw concepts, as networks of overlapping similarities. Here's how it works. First, we treat each data point as a member of a conceptual family. Then we compute resemblance scores between each point and its nearest neighbors, using functions like cosine similarity, log-based distance, or even kernel functions like RBF. These aren't just measures of closeness. They're measures of resemblance, how much one point resembles another in terms of shared traits. Next, we apply a threshold. Only pairs with high resemblance get connected. This creates a resemblance graph, where edges represent meaningful similarity. But here's the key insight. We don't need a single defining property. Instead, clusters emerge as connected components, chains of points linked through overlapping similarities. Point A resembles B, B resembles C, C resembles D even if A and D don't look alike. They're in the same family because of the chain. This is the core of WFR. Clusters are not defined by a shared essence, but by a chain of resemblance. And unlike K-means or DBSCAN, WFR doesn't require you to know how many clusters there are. It doesn't assume clusters are dense or convex. It can find spirals, rings, and even nested structures, because it's not measuring distance in a rigid way. It's measuring resemblance, which can be defined flexibly. Now, what about the threshold? That's the only hyperparameter, like a dial for how strict we are about what counts as a resemblance. Too high, and you get too many small clusters. Too low, and everything merges. But here's the elegant solution, automatic thresholding. We run a grid search over possible thresholds, and for each we compute two scores. Cluster separation, how well separated the clusters are in space. Cluster balance, how evenly the data is distributed across clusters. We maximize the sum of these two scores to find the optimal threshold. It's like letting the data itself tell us how many clusters make sense, not the user, not the algorithm's assumptions, but the structure of the resemblance network. And because WFR builds a sparse k-nearest neighbor graph, it's computationally efficient. Its time complexity is O, n log nd plus nk, linear in the number of edges. That's comparable to DBSCAN or HDBSCAN, but with far greater flexibility. You can plug in any resemblance function, cosine, RBF, even custom kernels. And unlike most clustering methods, WFR naturally supports out-of-sample clustering. Once trained, you can assign labels to new data by finding its most similar neighbors in the training set and checking if their resemblance exceeds the threshold. Let's see it in action. On the two spirals dataset, where clusters are intertwined and nonlinear, WFR with a log-based or kernel resemblance function correctly identifies the two spirals. DBSCAN fails here, not because it's flawed, but because it relies on density and metric balls which don't capture this structure. WFR doesn't care about density. It only cares about resemblance chains. On two moons, two circles, and even datasets with three overlapping Gaussians, WFR consistently recovers the true cluster structure. It detects outliers naturally, by labeling tiny clusters as -1, and adapts to complex shapes without tuning. And the best part? The algorithm isn't just effective. It's philosophically grounded. It's not just using Wittgenstein's idea, it's embodied it. The algorithm doesn't ask, what is a cluster? It asks, which points are connected by overlapping similarities? That's the essence of family resemblance. Of course, there's room to grow. Future work could extend WFR to weighted resemblance graphs, where edge weights reflect the strength of resemblance, not just presence or absence. That would allow for more nuanced clustering, while still preserving the chain of resemblance structure. But even in its current form, WFR is a powerful new tool in the unsupervised learning toolbox. It bridges the gap between philosophy and machine learning, what we call philomaths, showing that deep ideas from thought can inspire real advances in computation. So next time you're faced with a messy, nonlinear dataset, ask yourself, what if the clusters aren't defined by a single feature, but by a network of overlapping ones? Because sometimes the answer isn't in the data. It's in the philosophy. And now it's in the algorithm.